So we still regard you as, of course, an old colleague. But currently, Francois is a distinguished professor in climatology, as well as the director of the Global Change Institute of the University of the Witwatersrand. We know, and it's very good for me to confirm, of course, that Francois, you are a world expert specializing in climate model development and the simulation of climate variability and change in Africa and the Southern Hemisphere. I think you've always made the point of how important it is to include the Southern Hemisphere factors and contributions to the determination of models for the globe, as this is less studied than say the Northern Hemisphere. I can also mention in particular leads the development of the so-called variable resolution African-based Earth systems model, which is quite a mouthful, Francois. I'm not sure whether you're going to talk about that, but all I know is that it's trying to put everything into one model so that we can get the accuracy and the relevance up there to predict what we want to see. I just can also mention that as part of his involvement globally, he takes the lead involvement in several international collaborations. And I can just mention too, the Intergovernmental Panel on Climate Change, IPCC. Francois, I think you mentioned in your bio as well as the Assessment Report 6 Working Group. I think these are the bodies that we would like to contribute in this field, I would imagine, if you want to be recognized globally. And of course, I don't think you mentioned in your bio, but you were very actively involved, of course, very lately at COP26 in Glasgow, Scotland, at the end of last year, even if it's only on analyzing the activities and what is happening there and what it means for South Africa and the globe. But I can also mention you're, of course, very much a leading public speaker. I listen to you over the radio quite often, and I'm always quite amazed on how effective you are to explain relatively complex climate modeling and climate change and weather concepts to the general public. And I think this just shows why you are so effective as a public speaker. And lastly, maybe just to mention, of course, the connection to CHPC. And this is a long connection. I mean, you've been one of the key users, we almost like to say the true HPC users of HPC for climate model developments for a very long time, probably more than a decade already. And you've done this through several research programs, initially through the CSIR, but of course now continuing at WITS. So with that, Francois, I'm really looking forward to your talk. I see it's titled Convective-scale modeling on Lengau, so it seems very relevant to what CHPC is offering. So with that, over to you, Francois, and thank you very much.
Thanks so much, Werner. What a very kind introduction. Thank you so much. And yeah, it's wonderful that the CHPC also takes so much interest in the different domain experts working on the CHPC clusters. And I really appreciate that you know so much about the type of work that happens also specifically in the Earth system science space. But colleagues, I thought that I would like to talk today about what I think is becoming an increasingly important international frontier in climate modeling or Earth system modeling. It's known as convective-scale modeling. So I want to get to this in the talk because with also the director of CHPC attending today, I think this is an important opportunity for me to also make a case of this new infrastructural needs, computational needs that have now arisen in the climate modeling space. So I'll get to that. But I also want to make use of this talk to demonstrate to the CHPC how the resources they've been providing to the climate modeling effort in South Africa have been used, hopefully to good effect. I hope I can make that case today. I'm extremely grateful for their support. Our community, the climate modeling community, has been getting over the last decade. CHPC has really changed the scene for climate modelers in South Africa. About 10 years ago, it became possible to do things in South Africa we've never been able to do before, thanks to the CHPC resources. And of course, that capability has been increasing over time. So I want to demonstrate today what has been done and the impact that climate modeling in South Africa has had internationally, also in policy making over the last decade, and how that can be directly linked back to some experiments that have been performed on the CHPC clusters. So let me jump into this talk. I really hope that you are seeing it now in proper display mode, colleagues.
Francois, it seems not to be in full screen mode. Maybe you can just check again on your. It was right when I started to talk.
It's because I have all these different screens. So yeah, happy as
I think, Prof, if you can switch off presenter view. Prof, just switch off presenter view.
Okay. Okay, so if I go in here, then swap. Shall we go for this option? Yes. That's different, right?
Yes.
Thanks for whoever gave that hint. Thanks very much. That solved it. Thank you. So let me start to jump into this talk because I hope I have really interesting things to share. I would like to start by mentioning something very special that happened last year. More or less around the release of the IPCC Assessment Report 6. We, of course, also had the 2021 Nobel Prizes being announced, and the Nobel Prize for Physics in 2021 was shared by 3 renowned scientists. 2 of them were some of the world's pioneering climate models. So wasn't that a really very special recognition for climate modeling in that important year of the 26th Conference of the Parties and the release of Assessment Report 6? Now, there on the left-hand side of this slide, you can see the very famous Professor Manabe, originally from Japan. He was one of the Nobel Prize in Physics winners last year. And that was for some pioneering work he did in the 1960s on what is also the topic of my talk today, convection in the atmosphere. So that's the official statement that went out around the release, around the announcement of the reward he received. I'll just read the second sentence there. In the 1960s, he led the development of physical models of the Earth's climate, and he was the first person to explore the interaction between radiation balance and then, very important, the vertical transport of air masses. Now, that's what we call convection in climate science. And he, in fact, developed one of the world's first, or maybe the first, so-called convection scheme, also known as cumulus cloud parameterization schemes for climate models. And that is what I also want to talk about today, especially towards the end of my talk. So there you can see the paper published in 1964. What is this all about? Well, let me start by showing you yesterday's satellite picture. This was taken, I think, at 8 o'clock last night, South African time. And what you can see on this slide, all those globular, bright white shapes are thunderstorms. We are looking there specifically at so-called cumulonimbus cloud anvils. So it's a shield of ice crystals that form at the top of a thunderstorm. The thunderstorm itself is in fact substantially smaller than those bright white shapes that you can see on the satellite picture. But those globular white shapes represent the vertical, they are the consequence of vertical movement or convection in the atmosphere. And that convection plays a crucial role in the climate system because it transports large quantities of heat and water vapor right through the troposphere. So convection is really critical in terms of the heat balance, or we can say the radiation balance, and conservation of moisture in the atmosphere system and the atmospheric system. And from the earliest days of climate modeling, from the pioneering work of Professor Manabe until today, representing cumulus convection in climate models has been one of the biggest challenges, if not the biggest challenge in atmospheric modeling. The reason for this is straightforward. These are what we call fine scale systems, finer than what meteorologists know as the so-called mesoscale. A thunderstorm has a diameter of a few kilometers at most. The updrafts and the downdrafts in the thunderstorm, the real core of the storm, the dynamics of the storm, these aspects of the storm has a resolution in the horizontal, sometimes just in the order of a few hundred meters. And the problem that Professor Manabe faced back in the 1960s is that climate models were simply not able to resolve these systems. So remember, a climate model must run over the entire planet and resolve all processes, the ocean, the atmosphere in 3 dimensions. The resolution of climate models in the days of Professor Manabe was, there was one grid point. You can see grid points also on the satellite picture. In Professor Manabe's days, the grid points were spaced maybe 500 kilometers apart. Today, in 2022, or if we look at last year's assessment report, the resolution of climate models is typically 100 kilometers in the horizontal. There's no way the thunderstorms can be explicitly resolved in a climate model that runs for, say, 200 years, does simulations for periods of, say, 200 years in length. Not at a resolution of 100 kilometers. Why don't we run the climate model simply at a resolution of 1 kilometer? Well, we don't have big enough computers. Nowhere in the world is there a group that can do that at this point in time. So even the best and the best resource groups in the world presented in the assessment report 6 simulations in the order of 100 kilometers in the horizontal. That's how far away we are. Yet a new field in climate modeling is evolving, and it's called convective-scale modeling. And across the world, we are seeing the first pioneering simulations, just for short periods in time, where groups are starting to run climate models globally at a resolution of about 1 kilometer. So the first experiments are being done. Of course, in numerical weather prediction, where you just need to run a model a few days into the future, we are far closer to the convective scale. So the biggest and leading short-range forecasting center in the world is called ECMWF, European Center for Medium-Range Weather Forecasting. Their global short-range weather prediction now has a resolution of about 10 kilometers in the horizontal. Still far away from the convective scale, but they are approaching it in operational mode in short-range weather forecasting. So that's a bit of background of where I will eventually also end this talk. So I hope I've given a bit of background now in atmospheric convection. But let me now just first take a step backwards and give you an overview of where climate modeling in South Africa currently is, what we've been doing as a community in the last 10 years on the CHPC clusters, and then what we would like to do next at the convective scale. So that's what now awaits us in the rest of the talk. So I see we have many students in the talk, and I'm very, very happy to see some students from Wits and Northwest, and I'm sure they are from other universities as well. So what is climate modeling? Many of you in this talk will know very well what I'm talking about, but effectively climate models are based on the laws of physics, momentum, mass, energy, conservation. If you formulate those, if you apply those laws to the ocean and atmosphere, you find a very large set of partial differential equations. We need to solve these numerically on a discretized Earth, and that's where resolution comes into play. So as I've mentioned, the typical grid resolution now is about 100 kilometers for models that must be integrated for, say, 200 years into the future, a typical climate simulation. And the problem then is there are many atmospheric processes that cannot be explicitly resolved at 100-kilometer resolution in the horizontal. I've spoken about convection, but there's also, of course, turbulence in the atmosphere happening in the boundary layer, mostly at even smaller spatial scales. So always climate models will have to treat statistically those processes that cannot be resolved. And that is where uncertainty comes into climate change projections. Nobody knows exactly how to relate the large-scale features that can be resolved to the small-scale dynamic features that must be treated statistically. Nobody has a full understanding of those dynamics and then the cloud microphysics that actually function at the scale of water droplets. And that statistical treatment of these processes, that is known as cumulus parameterization. Professor Manabe was the pioneer who formulated the first of these statistical treatments, but until this day, it has remained a key source of uncertainty in climate models. So what can the climate models do that we are currently using? I'll just have 3 slides to briefly summarize this. For all the students, I can recommend, if you want to have a quick entry into the space of climate change projection, read chapter 4 of working group 1 of the IPCC assessment report 6. And that's where you will find all the most recent references about the projection of future climate change globally. So these models, of course, are integrated for different mitigation scenarios. So those are choices we are going to make as humans. This dark red line on this graph is a future where we continue to use fossil fuels. And there are various other scenarios depicted here. And at the other end of the spectrum, we have the Paris Agreement type future, where we do everything we possibly can to reduce greenhouse gas emissions into the atmosphere. So if we look at projections towards the end of the century, you can see that we really still have our own future in our hands as humans. If we do nothing, we will see devastating change, global warming approaching 5 degrees Celsius by the end of the century. We've probably left it too late to achieve this scenario. So most climate scientists and the IPCC has formally assessed that it is now more likely than not that we will exceed the so-called 1.5 degree threshold of global warming. But the report also said there's still enough time. We have an excellent chance of restricting global warming to below 2 degrees Celsius if we do start right now with a massive mitigation effort. So that's an interesting part of climate science, but it's not really the purpose of my talk today. I want to get more to these projections that climate models are generating. So what you are seeing now on the screen, that is the consensus result of about 40 different climate models that participated in assessment report 6 of IPCC. In this specific graphs, we are just looking at the projected changes in temperature patterns across the world as a function of different levels of global warming. And the main message here is that our region warms fast. If you want to find a place in the southern hemisphere that warms the fastest, you only have to go to Botswana. That's quite a striking fact, published by South African climate scientists some years ago. Under these low mitigation futures, where global warming reaches 3 or 4 degrees Celsius, I can only say, colleagues, it's devastating for us. There's no other word. 6 degrees of regional warming in Southern Africa is, according to the IPCC assessment on impacts made in 2018, likely the end of the maize crop in Southern Africa, and also likely the end of the cattle industry in Southern Africa. So that's a different regional world. And the young students in the audience, you may live into this world if the world is going to follow this low mitigation trajectory. At the same time, our region is projected to become generally drier. That's why we are a so-called climate change hotspot. We are a warm and dry region naturally in Southern Africa. Now we are projected to become drastically warmer and drier. That means options for adaptation are limited. Now, if you go and look up this figure 4.32 in chapter 4 of the assessment report, and you zoom into Eastern South Africa, and you look at these color scales that IPCC has assigned to the figure, you'll see something fascinating. There's one part of Southern Africa where it is not so clear that it is going to become generally drier. That's the Eastern Escarpment. For the Eastern Escarpment, climate models are giving a conflicting signal. We are not sure whether the future will be drier or wetter. And my assessment of that situation is that that is because the Eastern Escarpment, with its steep topography, is a region of spectacular convection. So those of you who have spent some summer days along the slopes of the Drakensberg Mountains, you would have seen beautiful and massive thunderstorms developing in front of your eyes in just sometimes 20 or 30 minutes. It's a major challenge for climate models, representing convection over South Africa's Eastern Escarpment. And the models are doing different things in their statistical treatments. This is a critical problem for us to solve as South African climatologists, because that's where we get our water from. The big mega dams are all located in the east. They all get their water from that Eastern Escarpment. So it's a critical problem for South African climate modelers to solve. Can we get more certainty about what's going to happen over the Eastern Escarpment? In a warmer world, how will convection be influenced? So, where are we in South Africa towards tackling that question? So, let me start to give you an overview of what we have been doing in the community to try and tackle this question and several others that are important to our future climate. I just want to list here a few highlights. Firstly, Southern Africa has been classified as a climate change hotspot by the Intergovernmental Panel on Climate Change, specifically in the special report on global warming of 1.5 degrees Celsius that was published in 2018. Now, if you go into the relevant chapter of that special report from IPCC, you will see that several papers produced by the Southern African climate community has contributed to that assessment being made by IPCC. I would like to highlight two important experiments that were performed on the CHPC clusters that contributed to this assessment. So I'll do that first, and then I'm going to come back to these other important highlights I want to report today to our Director of Research, Werner, our CHPC Director, Happy, and all the CHPC experts who have supported this work over the years. I see, for example, Charles on the call. Charles Crosby has been really a force behind F-system modeling on CHPC. And in recent months, of course, Mtetu Suvara, who has been giving us wonderful support. So I'm also reporting back today to all these colleagues. Let me start. I think the first important experiment was done back in the early 2000s. It was eventually published in 2009. This was the first regional climate change projection performed on a South African computer that simulated all the months of the year continuously for periods of for several decades in length. It was the first full climate change projection experiment performed on South African soil. And this was done on what I think was the first CHPC cluster. I think it was called the C4 cluster. Only Happy is probably the only person in this call who can remember exactly what that system was. But I've used it. This enabled the first experiment, and this was an experiment that demonstrated the dynamics the circulation dynamics of why Southern Africa is likely to become generally drier. So that was the first reasonably strong HPC system we had in South Africa, and it available, for the general, the broader research community. South African Weather Service, of course, always had its own system, usually a Cray type supercomputer. And from that experiment, of course, things started to grow. And back in 2015, we published, that was in my CSIR days, Werner has referred to, the first ensemble of projections of regional climate change performed over Africa. These simulations were performed at a resolution of 50 kilometers in the horizontal. We downscaled 6 global climate models for about 140 years each, 140 year simulation per model, per downscaling. It was the first ensemble generated at that point in time on African soil. So the first time we had a cluster that was able to do this type of calculation. And it became an important paper. It demonstrated once again, now looking at the larger ensemble, that Southern Africa is likely to become generally drier. East Africa is likely to become generally wetter. And at the same time, temperatures and extreme temperature events are projected to increase drastically under a low mitigation future. Now, from that baseline, we then continued and performed even larger downscalings in the years that followed. The next big experiment downscaled 12 global climate models, now for low and high mitigation scenarios. And these were published in South Africa's third National Communication on Climate Change. That eventually got published in 2018. The work happened in the preceding years, of course. But at the time of composing and writing the third National Communication, which is a key national document that gets submitted by the South African government to the United Nations Framework Convention on Climate Change. At the time when composing the document, this set of 12 downscalings of future climate change over Africa were it was the only set of dynamically downscaled scenarios for the African continent. There were also statistically downscaled scenarios generated by colleagues at UCT that were also important. That's a different approach. It has interesting advantages, most importantly, that it's computationally efficient. It also has some disadvantages, namely that to a large extent, you must rely on relationships that work in the present day that do not necessarily work for the future. So dynamic downscaling does not need to make such assumptions, but it's far more computationally expensive. So I'm thanking today the CHPC for making available the resources for these pioneering regional sets of projections performed in South Africa that I think really influenced national policy. The simulations were taken up first in the Department of Environmental Affairs, as it was called then, in its long-term adaptation scenarios project. And from there, it went into the third National Communication. And from that communication, the projections influenced what is today South Africa's National Adaptation Strategy. So this is as big as impact can be in South Africa. And without the CHPC, we would have had nothing produced locally at the time of writing these documents. It's only after this period of writing the third national communication that the international community, through the coordinated regional downscaling experiment, generated the first large multi-model ensemble of projections for Africa. So today we have about 12 international groups that have contributed simulations of this kind over Africa. So what has happened since then? Of course, we have to move forward in South Africa and try to stay, as the local community, a little bit ahead of what the internationals are doing. So in the last few years, we've been downscaling simulations at 8-kilometer resolution over East Africa and Southern Africa. And that has been using Lengau computational capabilities. I'll show some examples right now. But there are about 10 CHPC papers published, used by the assessment report from IPCC last year, and the Working Group 1 report, and some coming up in the Working Group 2 report that will be released at the end of this month. So CHPC has really had an impact, and I hope it is of value to everybody I've mentioned in CHPC to see that the resources actually found its way into the highest level international report on climate change and into key national reports on climate change policy. So what are we doing now, and how are we going to get to the convective scale? Well, all these experiments I've been closely involved in over the years make use of a very special Australian technology. It's known as the Conformal cubic atmospheric model. I've just been awake right through the night attending the International Conference on Southern Hemisphere Meteorology and Oceanography. It was supposed to be hosted in New Zealand, so that's why it's a strange schedule to follow. But overnight, I was impressed again by the extent to which this modeling system is being applied in Australia. It's now really everywhere in Australia. And it has been in South Africa and in several other countries for several decades now. It's really an international modeling system that is growing in its uptake by several climate modeling groups. How it works is the downscaling process. I won't give too much details, but effectively with this modeling system, the approach we prefer is that we take the sea surface temperatures and the sea ice from global models, and we use this to force the CCAM atmospheric model at its lower boundary, and we first integrate this atmospheric model globally after we have performed a bias correction of the coupled model, sea surface temperatures and sea ice. So we remove systematic errors from the global model simulations, the coupled model simulations, before we force the atmospheric model with these corrected fields. That leads to better present-day climatologies, better than those of the host coupled models. This is a bit technical. Maybe if we have questions afterwards, we can talk about that. The next step is then where the downscaling really starts, because once you have this global simulation, you can then use it, of course, to drive finer scale simulations over smaller areas. The modeling system that we use is a so-called stretch grid global model. So the same global model becomes a regional model by stretching its grid over an area of interest, but the model always runs globally. And that's a big advantage over traditional so-called limited area regional modeling. So the climate modelers attending today will know exactly what I'm talking about. So if we stretch the grid, we can of course concentrate grid points over our area of interest. And in that way, it has become achievable on the Lengau cluster to perform long simulations of typically say 200 years in length at 8-kilometer resolution at areas of about 2,000 by 2,000 square kilometers in dimension. And that is what we can, with reasonable comfort, achieve now on the Lengau cluster. So how do such 8-kilometer simulations look like? They are starting to resolve convection. So I'm getting now a little bit closer to my talk. They can start to resolve the we call these mesoscale convective complexes that are so important in South Africa's climate. These big thunderstorm systems that move in almost always from Botswana into Northwest Province, sometimes into Gauteng and the Free State. These types of systems are big enough to be partially resolved at 8-kilometer resolution in the horizontal. And you can just see the wonderful detail of our rainfall climatology as reproduced by 8-kilometer resolution simulation. These are aspects you'll never see in a global model simulation of 100-kilometer resolution in the horizontal. For example, here you can see in the southwest, actually I have a zoom in of this, the Cape Fold Mountains with that orographic rain that occurs when cold fronts move over this region in winter time. Also the influence of the west to east aligned Cape Fold Mountains in inducing high rainfall totals over parts of our Cape South Coast. And then, of course, most importantly, the Eastern Escarpment with all the convection it receives in summer, well resolved at the 8-kilometer resolution model grid. We've used this setup to also generate projections of future climate change for our region at 8-kilometer resolution. This was the second generation experiment. It downscaled about 6 coupled models from the fifth, related to the fifth assessment report of IPCC, or the so-called coupled model intercomparison project phase 5. The first generation of these supported the so-called CSIR Green Book, which has become our most important resource for municipal planning in South Africa. So planning at the municipal scale for climate change risks. That was a really grand CSIR project completed roughly 3 or 4 years ago. The second generation of simulations were part of a big future Climate for Africa project with partners from the University of Cape Town, the so-called Fractal project led by colleagues at UCT, which was really a pioneering project in climate services. And these are the simulations that supported that project. You can see once again, the general picture is one of drier conditions for Southern Africa. But just have a look there over the Eastern Escarpment, there's something different happens. So here the downscalings were all, to some extent, indicative of rainfall increases, sometimes quite substantially so in some of the downscalings over this important high altitude region. You can see some downscalings are indicating much drier conditions over Mozambique in the future, but others are indicating rainfall increases. That's another example of model uncertainty. And this relates to another important aspect, tropical cyclones. Global climate models cannot resolve tropical cyclones. They have something that we call tropical cyclone-like vortices, but they just can't resolve the convection, the thunderstorms, the cloud wall around the center of a cyclone. So the global model projections force these regional simulations. So the regional simulations are always compromised by that uncertainty in the global models. So we really need to get to the point where the global models themselves become convection resolving. So what are we doing now at even finer resolutions? Well, currently I know of at least 2 important experiments that are running in South Africa on the Lengau cluster, where climate models are integrated at 1 kilometer resolution in the horizontal. The one experiment is the one I'm showing here on the grid on the picture, the grid on the slide. It's a simulation performed over the Nkangala Escarpment of South Africa, so the more central to northern Drakensberg. The domain only stretches over 200 by 200 square kilometers, but this simulation is resolving thunderstorms. So it's a fascinating simulation. It is work done by a PhD student of mine at the Global Change Institute at WITS. Many of you will know Abu Bakr in the climate community. And I'll suggest to Daniel at some point in time that Abu Bakr presents on his pioneering simulations. The other big experiment is one run by Robert Maisha of the South African Weather Service. He started with this work when he was at CSIR, and he's resolving urban heat islands in South Africa at 1 kilometer resolution. So those runs are also convective resolving, but it also resolves urban heat islands. So that's another fascinating experiment. Robert studies with Tandu Ndagana at UP, and I hope we can also invite him at some point to report to the community on his pioneering experiment. He and Abu Bakr are finishing their PhDs this year. I don't want to steal their thunder, and I won't report on too much details of their work. I'll rather show another experiment, another convection resolving run that we are now currently conducting at the Global Change Institute over Lake Malawi. Fascinating. So Lake Malawi has rainfall maxima that has never been fully understood. And we now have domains over Lake Malawi at 8-kilometer resolution and at 1-kilometer resolution as part of Horizon's 2020 project. And what you can see in this specific simulation is how the climate model resolves thunderstorms that form on the edge of a lake breeze that develop in summertime around Lake Malawi. So that's quite fascinating. That line you can see on the western shore of the lake is the result of convection that form when the lake breeze flow from the relatively cool lake to the warmer land surface around Lake Malawi. And this work we are doing to understand future lake levels, the future levels of Lake Malawi in a changing climate, which is of course critical to the local communities and also for the growing hydroelectricity sector in Malawi. So let me conclude. I hope so that we can have a bit of time for questions. I think I only have these 2 slides left. So in summary, thanks directly attributable to the capacity that CHPC has provided to the climate modeling community in South Africa over the last 10 years. I think we have a growing climate modeling and climate model development community in South Africa. Of course, here at the Global Change Institute, we are leading and we are very much focused on building an African-based climate model. And our goal is, of course, in the first place, projecting our climate change futures for the continent. And you can see from the few examples I've shown, our focus at the moment is really very much on Southern Africa and East Africa. Here at WITS, of course, there's a big focus on understanding where we are coming from as humans. So the evolution of hominins and early modern humans is an important study field at WITS with the rich fossil record at the cradle of humankind that many of you will know of. So modeling paleoclimate is becoming an important focus for us at WITS and at Global Change Institute. And of course, if you want to build a model like this, you need excellent people. So building a new cadre of postgraduate and postdoctoral students studying climate modeling in South Africa. Of course, for a university, that's a very big goal. This has been very, very generously supported and funded by the National Research Foundation. All this model development work has direct support through students and some infrastructure support coming from the National Research Foundation. So I should also thank them today. This is about a partnership, everybody. I don't think there's a single institute in South Africa with the critical human capacity to do this. So the work I've been reporting on today has been part of this NRF project, which was a collaboration between WITS, very important CSIR, the Carbon Modeling Group, the SOCO, the Carbon and Climate Observatory at CSIR, Pedro Monteiro's group. Many of you will know Pedro. I think Nicolette is in the seminar. UCT, Marcello Vicci's group, sea ice modeling. That's an important contribution, I think, increasingly important in the future of this F system model. Of course, the Australians will always remain our partners. And then the most exciting recent development is a growing collaboration with the Weather Service. Mary Jane Bopapi's efforts, of course, I think is well known to advance climate modeling in the country. And I think there will be a growing collaboration between the climate-based efforts at WITS and the source efforts, which of course contains another important, very important field, namely the numerical weather prediction and seasonal forecasting aspects of climate modeling. The very last slide, and this is now my slide designed specifically for our CHPC director of research and the experts at CHPC. this, colleagues, is what the international community is heading towards. ECMWF, the biggest and best resourced center in the world, are heading now for numerical weather predictions at a horizontal resolution of 3 kilometers. So routine weather predictions at that resolution. They are envisaging a 1 million core system for this purpose. So that's, of course, a massive budget. Climate modeling is heading towards systems greater than 1, that offer more than 1 exaflops. Storage is now typically, in this new generation of systems, in the order of 250 petabytes, just for tailor-made climate modeling applications. The costs, the World Meteorological Organization estimate is 300 to 600 million US dollars for such a system. The carbon footprint is becoming an issue for these types of systems. There's a thrust to try and make these systems in some way carbon neutral by 2030. That's another thrust. Can it be achieved? But what we need in South Africa is we need to get to the convective scale, not only at areas of 200 by 200 square kilometers, as I've mentioned, but actually over Southern Africa or over Africa. Now, I've done a calculation some months ago of what we need to perform climate simulation, no 100-year in length simulation at this scale. And if you carefully look at how these models are scaling and how the time steps that they require for these types of simulations, we do need an order of magnitude larger capability in South Africa. So if you really want to simulate at a continental scale, where you are resolving convection, colleagues, we will draw the attention of the world to Africa if we can do that. If Africa can produce a continent-wide convective resolving simulation, I mean, at climate change timescales, not for a few days. That's already tough, just to do it for a few days. But I think typically we are looking at an allocation of about 6 million core hours per year, 60 million core hours per year to really do this type of research. And there must, of course, be a production component to produce the projections themselves. That's an immense challenge. But we know CHPC has changed the equation in South Africa over the last decade. And I have all confidence in the leadership of CHPC that they will once again change the equation so that we can compete with the international community in these types of simulations. And really, if the African modelers are not going to tackle African convection, I think it's going to take very, very long for the international community to tackle this problem on our behalf. It will be wonderful if we can take the lead. We have the domain expertise. We have the local data sets. We have the climatologists that understand the African climate. It's a problem up for the taking for us if we can just get the computational backing behind us. So with that, Werner, I return the floor to you, and I hope there's time for a question or two.
Francois, thank you very much, as always, and as I almost predicted in the beginning, a very clear talk presented that even I could understand it, so then it's real achievement. I think bringing this specific topic of convective scale modeling and what it means within the broader, say, climate model developments is interesting. And I think I can understand why you chose it, because it's all about reducing resolution, or well, increasing resolution, making it finer and finer grids. And the moment we start talking in that direction, you need more and more compute. So this is a clear message, and I think you couldn't have spelled it out more clearer than in your last slide. So because that would have been my question in any case. You are presenting fantastic work, and the CHPC is very pleased to be part of this in various ways. But of course, we would like to be even more part of this going forward. And as we plan to increase our own compute resources, these are typically the projects that we would like to see. And I can just mention to the audience that when Francois now starts talking about 60 million core hours per year, Francois, that doesn't scare us too much. I think this is the kind of thing that we probably would be able to start doing with our new resources coming. So I'm pleased to, well, at least from our estimates, I think these are the kind of things that we will be able to provide, and we can start doing those additional runs that you need. So yeah, thank you very much.
Thank you, Van. I'm getting goosebumps when you are saying 60 million core hours is within reach. That's amazing. So that gives me an idea of what you are planning here at CHPC. But I'm not too surprised, because I know you are always pushing the field ahead on behalf of the computational community in the country. So thanks for that. And yes, Van, I mean, the idea is that increased resolution will result in decreased uncertainty, because a process that we have no choice right now but to treat statistically, we can resolve explicitly. That should give us a reduction in uncertainty over these important convection-prone regions in Africa.
Yeah, maybe just to also for the audience benefits, our biggest programs at the CHPC at the moment, and there's only a handful of them that really can use the hours productively, touches around 6 million hours on a 6-monthly basis. So you can see that is more or less where we hit the limit at the moment. But I think with our new system coming, we will be able to present the users that really need it with that. I have 1 or 2 questions on the chat, but I see Happy's hand is up. Dr. Happy Sitole, you can proceed first, then I will get back to the questions in the chat. Thanks.
No, thank you very much, Werner, for the opportunity. And Francois, thank you very much for a very good talk. That's opening our eyes. And, you know, I don't want to say this is a talk, this is a lecture. Sitting there and going back, you know, to the geography and understanding of climate modeling. I think that's what you managed to achieve. And my younger colleagues on the call here, I guess they will share the same sentiments. And yes, I think the path that you also put in, those are some of the things that we expect to hear on these seminars. Basically to be able to tell us on various fields, where are things going? Because what we'd like to do, we'd like to be able to predict and be able to start planning for the resources and the proper support. And I think this talk achieves this very well. Coming to your last task, I think as Werner has already indicated, our plan for the resources is always based on what the community wants to achieve. And I have been, you know, indicating that the bioinformatics, climate modeling, and astronomers are people who are not shy to tell us where they want to go. And we always plan around there. And what we have just put as a challenge now, I think we need to start working on it. And I'm going to request my colleagues to start looking at this, because one of the things that we want to achieve is with every machine to be able to have like a flagship computation that takes place on that machine. As much as we run LeanPack as a benchmark, so we would like to also have a real application running on the whole system. And these are some of the things, as long as it is planned in advance, so that the other users know that for a certain period, the machine won't be accessed because it's doing a specific duty. And I would like to engage my colleagues now that they must think about this and set up a time where we can dedicate either a day to Lengau to do this benchmark of this computation. So that even with the next system, we should be able to check. Because when we say we need an exaflop, we need to be able to show that we can completely use the 1 petaflop that we are doing. We can completely use the 4 and 10 petaflops that are being anticipated, so that the business case for a 1 exaflop is well articulated. And And I trust your climate modeling simulations to give us that test. And it will be over to you, Werner, Dora, Charles, and the other colleagues to see how do you arrange that, so that probably that could be something that we can report back on as Lengau is gracefully trying to limp out of the data center, that it can still be doing some very interesting science. So I'm looking forward to that. Thank you very much, Francois.
Thank you so much, Happy, because I think I'm not surprised that you're now also putting a challenge to the climate modeling community, and we greatly appreciate that. And I think we can jointly tackle this challenge. And of course, an African scale convection resolving simulation would be an immense accomplishment for a computational capability on African soil. The reward that we will get is that we will also demonstrate to the international community that we mean serious business in terms of taking forward African climate change science. So we can definitely also contribute to this effort and set up a well-designed control experiment. And it will be an excellent challenge also in terms of scalability of the code. And I think with the development work we've been doing on this code, increasingly also in collaboration with the Weather Service, and of course with the Australian partners, we have a code that we think will scale very, very well into tens of thousands of processes. It has, of course, never been tested there. We've never done that test, but it should. We anticipate that it will scale very well on such a system. So I'm looking forward to work with CHPC on this challenge. Thank you so much, Abby.
We are ready, Francois, for the follow-up discussions. Let's just have a look at one or two questions there in the chat. Francois, you might be able to see them yourselves. The first one is from Debbie Jewett. Good morning, actually probably good afternoon. Thank you for a very interesting presentation. Is the 8-kilometer downscale data available for download and use?
Yes. Yes, thanks, Debbie. So the last version of these 8-kilometer resolution CMIP5 downscalings, they were generated through this project I've mentioned that was led by our colleagues at the University of Cape Town, the so-called Fractal project, which formed part of the Future Climate Change for Africa project. And in that project, all data sets are available for public use. The previous generation of data sets generated through the CSIR Green Book project is also available to the public for the largest possible uptake. That's a good thing, I think, of this type of research. It has always been undertaken with public goods funding, and therefore it should be generally available to the community. So to get hold of those data sets, the easiest may be if you just drop me an email and I can put you into contact with the relevant sites and service providers from where this can be obtained. Now, there's also the new set of scenarios, downscalings of CMIP6. And this is a new project starting soon under the auspices of the Southern African Climate Services Center, SASCO, in Windhoek. And the plan is for those simulations to be available through a SASCO data center that will also be developed over the next few years. So there are plans to also make the next generation freely available. I personally have never tried to sell this type of data. I'm absolutely against selling climate data. My wish is that the international community will increasingly share all types of climate data, because that's the best way to take the science forward. But yeah, to answer your question, these specific simulations are available for general uptake and use.
Thanks, Francois. I'm not sure whether you've addressed Frederick Mashaw's question already, but he's asking about the difference between the statistical and dynamic downscaling and which one can you recommend. And then he also talked about lack of the downscaled climate data hindering efforts to come up with accurate local climate risk vulnerability assessments. And again, where can we freely access this data. So I don't know whether you want to respond a bit further, maybe on the first part first.
Sure. Yeah, so thank you for that question. I think dynamic downscaling, which uses mathematical models based on the laws of physics, has certainly become by far the dominant downscaling method worldwide. So almost all the Codex projections, detailed downscale projections available internationally, have been produced using dynamic downscaling. The main reason for that is that you simulate future climate using the laws of physics. So you simulate that from first principles. You have to have a computationally strong system to be able to generate the projections. That's the disadvantage. It's really expensive computation. Now, statistical downscaling was really important in the early days of climate change projection when we didn't have these types of computational resources. This is a far simpler computational method. Fundamentally, you find the relationship that exists today between these low resolution circulation fields that the global models can resolve, like weather patterns at synoptic scales, and then observations of rainfall at the finer scale. So if you have fine scale rainfall observations, you find a statistical relationship between those and the large scale fields the global model can resolve. Then you assume that that relationship remains valid into the future. And then when a model projects, even at low resolution for you, future circulation patterns, you use the statistical relationship to deduce the fine scale rainfall patterns. There are two disadvantages to this approach. I've mentioned the one earlier today. The second one is you can only do this if you have high quality, fine scale observations. In many parts of Africa, we don't have them. We just don't have such an observational network. Remotely sensed precipitation data sets are available, but such data sets are not really available for other variables such as tropical cyclone intensities or temperatures or fire outbreaks. So observations limit, the lack of observations always limits statistical downscaling methods. The other problem is that relationships that are valid today between large-scale circulation fields and rainfall will not necessarily remain valid into the future, because remember, the climate system is changing. The circulation regimes are changing. The thermodynamics are changing. That is the fundamental weakness of statistical downscaling. And I don't think the method will be with us that much longer. Increasingly, we are going to see convective resolving climate models, first over small areas, then over larger and larger areas. That will be the dominant method of downscaling over the next decade. I'm quite convinced about that.
Thanks, Francois. Yeah, we're running a bit over time, but I think we can maybe end off with the two last comments. The one dealing with GPUs as a computational resource, and the other about machine learning. So maybe Anton Lopez is asking, will the codes or the models ever be suitable or able to benefit from GPU? Of course, most of the really important runs requires thousands of cores. Yeah, is there any talk about GPU? I see Nteto made a comment there about ideas for CCAM, but maybe in general from your side, what is the picture? Or
yes,
how you see it?
Yes, Werner. Yeah, that's another important question. The field is evolving rapidly. In the biggest climate modeling centers in the world with a lot of human resources, climate model codes have already become a mixture of CPUs and GPUs. There are many parts of a climate model code that can be sped up during integration by using GPUs. For example, in a climate model, you always have the fascinating aspect that one part of the world is getting sunlight and needs to interrogate solar radiation moving through the atmosphere. Whilst the other part of the world is not having sunlight, and processes are much simpler computationally on the other side of the globe. So there are clever ways to deploy GPUs to look after certain parts of the physics of the numerical solution procedure to speed up the solution on certain parts of the globe. I have a little bit of expertise in coding parallel codes, but only on CPUs. I've never had the time to venture into building GPUs into our code myself. But the Australian partners have a somewhat bigger team, and they have now a first GPU capability, really unexplored, but a basic capability embedded in this specific code, we are using on CHPC. So colleagues, if there are some of you with speciality in this field and with interest to help us exploring this aspect of the code, we will of course welcome such collaborations.
Okay, no, that is good, because the CHPC, of course, we don't have a lot, but we have dedicated GPU resources that is quite heavily utilized, but we can certainly help in even if it's just about testing to see what we can do. So that's a very interesting comment. Thanks, Francois. So let's maybe end off with Krishna's question. He's asking about, have there been any machine learning attempts in predicting these climate models? If so, how accurate have these been?
Yeah, so I'm getting all the exciting questions today. Thank you, Krishna. Krishna, the field is exploding. So there are already attempts to build climate models that are entirely machine learning based. It's a brand new field. Everything that is being done at the moment gets published because it's really new. In recent applications, machine learning techniques have been used to deduce the fundamental equations that govern atmospheric motion by interrogating how atmospheric circulation fields evolve over time. So that was a fascinating study published recently. But my own prediction, and I'm often now in international groups discussing this aspect, what I think is going to happen is that climate models will remain fundamentally based on the laws of physics. They will remain fundamentally dynamically based because we know the laws exactly. So why would we attempt to solve for these relationships indirectly via machine learning techniques? But I think machine learning will increasingly become a way to do parameterizations within climate models. Yeah. And the exciting thing is there are already 2 users on CHPC. There are 2 students from CSIR registered here at WITS that are part of Pedro Monteiro's group at CSIR, the soccer group. And they are exploring machine learning techniques in terms of, in the case of the one student, parameterizing the effects of sub-mesoscale eddies in the ocean in the climate model with a machine learning method. I've spoken about convection. The equivalent in the ocean of that is the sub-mesoscale eddies, specifically in the Southern Ocean. It's a fascinating project right at the edge of this developing field. So we are building the first machine learning parameterization for this type of movement into the African Earth system model. So that's exciting. And we have another student that are learning more about the attributes of these systems by using machine learning techniques. So I think increasingly we will see machine learning methods being blended into the actual climate models and used to interrogate the output of the model.
Yeah. That sounds fantastic, Francois. I mean, it also links back to the GPU question, because when it comes to the training and inferencing of those models, GPUs might also be the way to go and to contribute then in an indirect way. But I think, Happy, you want to make a comment?
Yeah, no, I wanted to add on the comment by Francois, and indeed, not just for climate modeling. We see a lot of machine learning in many other simulation domains and mainly being used for parameterization. And this is what takes a lot of efforts. For an example, Krishna will know in material science and chemistry, when you are looking at various other combinations or polymorphs or even atomic positions, one of the ways of optimizing this is go on machine learning and look at various configurations before you go into the actual solution of the problem. So it is increasingly being used in most others. But specifically also about one project, and this, I'm not sure if Mary Jane is on the call, I haven't checked, but we are currently, Francois, you might also be aware of this, putting a proposal for the BRICS. This has already gone through the first stages. It has been approved for the first stages. So we're hoping this is going to be one of the flagship projects in the BRICS. And it is mainly looking at that where we're working together with the Russians and Brazil, and now India and China have joined. And specifically, it is looking at bringing in machine learning into the climate models. And the current problem that is being solved, they are looking, because we're looking at a common problem in the 5 BRICS countries, and this was more around flooding. So, but Mary Jane, you can reach out to Mary Jane. Oh, Mteto is also part of that discussion, so they can give you more details on that. And I think we are going to need more people outside climate modeling to start tackling that problem. So, Krishna, you're welcome to join the team. So.
Excellent.
Thank
Thanks,
you.
Happy. Yeah. I
Thank
have some involvement there, thanks to Mary Jane's efforts. And no, I fully agree, colleagues. That is yet another growing field, machine learning in climate models. We have to be part of this international effort in South Africa.
Yeah, thanks, Francois. I think we're going to end it there. If anybody wants to ask further questions of Francois, we can make the communication and email address and so on available. But thank you, Francois, for this very interesting talk and the discussion. We appreciate the role that CHPC can play in the success of what you are doing. So thank you also for bringing this message to a broader audience. This video is recorded, so it will be available for anybody to view at any time. And Francois, if you want to post it somewhere where you would like people to access it, you're most welcome. So thank you very much, and I think we're going to end it there. So thanks, and enjoy the rest of the day, everybody, and you as well, Francois. Thank you very much. Keep well.
Thanks so much, Werner. Thanks for the questions, everybody. See you around.
Okay. Bye-bye.